And I'm going to talk about basically my experience using Bayesian methods in the context of software engineering. All right. Yes. So software engineering is pretty big, and what I do is pretty simple: is I run programs and I measure how long it takes, and then I have a few knobs to turn, and I turn them, and then I see if it makes things faster. So one metaphor for this is if you're, I know some people come from the health kind of sciences. So the metaphor that I usually use is that you have someone who runs a race and you want to see what kind of influences how fast they run. So the kind of data that I get is I have some optimizations that I can like turn on and off, and I have a base program without all the with the optimization turned off. Then I have the different hardware that I can run my program on, and then the response, I get the execution time, so the time it takes to run the program. The reason I use this metaphor for like running is because there's a concept called warm-up, which is that if I run my program, it runs faster and faster if I run it several times in a row. Okay. The types of questions that I have is like what kind of effect does the optimization have, and is this effect influenced by other things? So like the warm-up and then the machine architecture or whatever. So to illustrate the warm-up, this is a plot of a program that I'm running. So I run it in two kind of laps. So I run the program once and it runs like fully, and then I run it again. And when I run it again, it runs faster the second time. And then as I keep doing this, it runs like faster, faster, faster until it reaches some kind of plateau. Deciding exactly when we reach this kind of what we call the steady state of the program is kind of tricky. But the way we do it in our community is that we consider those. We don't try to like make a prediction for the whole curve, but we try to consider them as discrete things. So you can say I have startup performance when like the program is so-called cold, and then I have like the hot phase where it's like or steady state. Right. Okay. So then I have my data, and then I go to look for like how should I do this? This is one paper that's fairly well cited in the field, which explains how do you do Java performance evaluation. And the suggestion from this paper are to use, if you have two options, you can use confidence intervals, and they explain how to complete those. If you have multiple options, you can use an ANOVA or MANOVA. And if you want to know which variant is the fastest, they have like some tests that they suggest, so 2K HSD in this case. Right. So what I did is I took my data, I put it in my ANOVA, like in R, and I get this ANOVA table. And the problem that I have with this table is that I don't understand any of it. Right. So, and the biggest question I have about this is that I still don't understand if it's the same as linear regression or not really. Well, I couldn't really go very far with this approach. So yeah, this is actually something that they acknowledge in the paper. They say the output is often non-intuitive and in many cases hard to understand without deep background knowledge in statistics. So another approach is to use Bayesian methods, and that's why I'm here. And so it's partially like I'm going to talk about like one paper that we did where we make a Bayesian model for like performance analysis, and it's based partially on that paper that was published in 2019, and mostly on this book that maybe people have heard of. It's really nice. I like it a lot, so that's why I brought it here. And this is the paper that we presented at a major conference in the field. I know that conferences don't have the same status perhaps in life sciences, but in computer science they are at the same kind of level of prestige as, let's say, journals. But I still presented it in the new ideas and emerging results because the community doesn't really know about Bayesian methods that well. Okay, so there are three reasons why I think this is nice, and this is what was cited, was mentioned in the paper that we also took inspiration from, which is that the Bayesian approach has the advantages that it's more explicit, so it's easier for me to check what the model actually assumes. It's more flexible, so I could change my model and like change things, and it still works. And in my view, it's more intuitive because I have fewer concepts to learn. So the basic model uses two distributions that you probably already know, the normal and the exponential. And the basic model is fairly simple. It's just a Bayesian linear regression. So in R, this is what you would do, like if you did a frequentist regression, you have the full model at the top, which is I take the log of the execution time because I'm interested in differences in percentages and not in like milliseconds. And then I add one factor for like what machine I'm using, if the machine is like hot or cold, and what kind of optimization are going on. And at the lower, what I have is basically the same specification, but kind of in the Bayesian way. Yes, I don't have time to talk a lot about the different kind of like how I set my prayers and so on, but this is the end. All right. The next thing about this, the one thing that I appreciated a lot is that if I want to know if the model assumes normal residuals, it's here in the model. And I can see that they use common parents for all the residuals. And that's, I don't need to, like compared to the frequentist approach where I just get like perhaps a test with some guy's name. Instead, I can look at the model and know what it does. Right. The implementation is a tool that perhaps not everybody is familiar with. This is a library called Turing for the Julia programming language. It's quite nice. I like it. I tried it with Stan, and the inference was faster, but it was a bit clunkier to specify the model. So in the end, I chose to stick to the Julia. Right. One nice thing I liked about this as well is once I get my chain, if I want to compute, like let's say, difference between effects, I can just take the samples from the chain and do like minus between the vectors. Which was really nice compared to the like least squares case where I have to do like think about, okay, how do I want to encode my categorical variables, and there's how do I interpret what the interaction coefficients mean, and so on and so forth, which is quite hard, I thought. Yes, because so in my field, most of the like factors that I have, they are discrete, so it's like and they're not necessarily ordered. So in one case, I can have like the original program and then the optimized version. So there's like a clear base. So I would use like dummy encoding for this. But sometimes for the machine, there's no base machine. It's just like red, green, blue. There's completely like unsorted kind. All right. Then the nice thing about this is that I could also extend the model. So if I want to do something like ANOVA, there's a paper by Kelman where what they do is that you use a hierarchical model to compute what kind, like the importance of each factor for your analysis. And the way you do this is that in my analysis, I have three arrays of coefficients, right? So I have one for the different machines that I can use. I have one for each machine. I have one coefficient for like whether my program is hot or cold, and then I have one factor for each optimization. And if I want to know the importance of each of those factors, what I can do is try to estimate their standard deviation within the vector. So then I can go back to my model and think, okay, how do I estimate that as well? And the way I estimate this is that, for example, on the third line, the alpha m is like the effect for each machine. And what I can say is I want to measure the standard deviation of that. So I add a new kind of latent variable that says, okay, this is from normal with the standard deviation, but I don't know it. And then because I add more latent variables, I need to add more parameters. But that's basically the rule about it. All right. And then I can run my model, and I can show, for instance, that at the top, this is the difference between the optimization and the base. So I can see that the first optimization slows down the program by about 10%. And then the second optimization speeds it up by about a bit more than 5%. And at the bottom, this is the posterior distribution. I did the credible intervals for the posterior distribution of the different like sigma terms in my model, which allows me to say that there's quite a lot of differences between the different machines and between the effect of like warm-up. So warm-up matters quite a lot. So when you warm up, it runs significantly faster. And that matters more than the optimization that I have. One thing that we also added in the model that we present and doesn't seem to be that well known is that I can have interactions where I can check if an optimization works only in some cases. So here I can make this plot that shows basically that in the first case, when my program is basically called, the optimization makes the program worse. But as my program warms up, then this effect disappears. So it becomes pretty much the same as the original program. And in the second case, what I can show is that at first, once you're at first when the program is called, the optimization doesn't have an effect. But then as it warms up, the optimization kicks in and then it has an effect. Which to me was like mind blowing that I could just pour my data into this and then I get those results. Cool. The way I do this, but I won't go into that much detail, is that instead of having an array, I have a matrix, and then I take care about the indexing with the different discrete problems. All right, and then I can do my own modeling because I can have like the different. I can measure the standard deviations of the matrices and so of the different elements of the matrix. Cool. Yeah, and then what we conclude is that the machine matters a lot. The warm-up also matters a lot. There is quite a strong impact, like basically the optimization, the interaction between the optimization and the warm-up kind of matters. But then, for example, we see that the interaction with the machine doesn't matter. What I mean by that is that if an optimization works on one machine, we show that it would work on the other as well, which is cool. So my conclusions about this experience is that it was great. And I get the benefits that were listed in the paper, which is that it's more explicit, so I can look at the model and I get like there's no hidden. I have what it says on the test basically. I have everything I want to know about my model. It's very flexible, so I can start with one model and then I can change things to as I have more questions, and it doesn't break everything. I can like keep working with this, which is great. But the main drawback is that it's pretty slow. So if I run the classical linear regression, it takes 1 millisecond, and then if I run the MCMC sampling, it takes 353 seconds. So I went a little bit. This is not to look like for ways on how to make this faster. I haven't really listed this in the paper. Here are two like things to make quick like checks in the model. So you can. With the Turing library, you can ask for the maximum a posterior estimate. So for each latent variable, you get one single number. That's like the top of the posterior distribution. The nice thing is that it's really fast. So then I can check if there's obvious problems with my models. Meaning like if I forgot to index the thing in the correct way and things like that, then I can check that it can work. I don't get the full distribution, which is kind of, I'm still interested in that, but it's still a good like quick check. There's a second thing that I looked a little bit into, which is variational inference, which is basically trying to do the inference, but by you have some additional assumptions that kind of make an approximation. And well, two things I can say. First, at first it looks very scary, but overall, it feels like, okay, it's mostly like you make some assumptions that tries to compute an approximation. So it's not exactly what you're looking for, but it's kind of close-ish. But that's the close-ish part that I'm worried about. So I guess in the end, what you would like to do is still run the full like MCMC sampling to be sure. But it's good to make like quick checks. I wanted to conclude a little bit about like the state of maybe statistical methods in my area of software engineering. So Bayesian statistics are relatively new. I mentioned this paper that was published in 2019. So it doesn't. I don't think it got much traction so far. In terms of design of experiment, while I was reading about this, I feel that the health sciences are way ahead in terms of what they do. In our case, what we do is that randomization isn't really a thing. What you do is that you say, okay, I put like 4 loops and then I run my program 16 times and then we're good. Like we don't care about like what kind of order you run, like if you have to change the order in some way or anything like that. That's not really something that I've seen. So what we try to do to remove this kind of the kind of like if you have like noise that could bias your results, what we do is that we just try to remove that. So look into the program if you don't have like background tasks and like to look into the computer, but it's quite hard. So yeah, that's one thing. The one community does that, and then there are people who know machine learning who just do Bayesian optimization for everything. So they don't really plan experiments. They just say, okay, I'm going to take a Bayesian optimization library, and there we go. Yes. Lastly, what I wanted to talk about is causal inference, because I think it's very interesting. And this is like, if you want to talk to me about something, maybe this is it. Because I'm really interested in this. So this is kind of like an example that was in one paper about kind of like performance analysis, where they say, but if you test an optimization, but then you test it on 2 different machines, and like you basically the machine has an influence on which optimization you're running, then you might bias the results. And you can show that with this graph, which is basically confounder bias. But they don't talk about it this way. They talk about it in English, as like, oh, this would be bad. But I feel those graphs in like causal inference are super useful and super informative and super compact. And I have this kind of feeling, but I'm not sure if I'm correct, because to me it feels like if you have a causal graph, it tells you about how you should plan your experiments. And that when you plan experiments, you're trying to like manipulate the graph in some way. So for example, like when you randomize, you try to make sure that some edges don't exist, because you want to be sure that those 2 are not correlated with each other. So we can like make causal estimates, but I'm not sure about it. Right. Yeah, lastly, there is some work that tries to use causal inference. This is from a review of the use of causal inference in software engineering, and what they say is that it's kind of small. And I think it's like basically people talk about this a lot less than they do in the hard sciences. So you have lots of like kind of initiatives, to talk about that in the hard sciences, but in software engineering, it's kind of like, okay, that's a thing that people do, I guess. Yes. So these are my takeaways. Overall, it was good. It's nice. I like the idea that again, like the model is very explicit, it's very flexible, so I can just like change things and things that works. It was, in my view, way more intuitive than what I got from the frequentist literature, I would say. But then I think that like software engineering don't use it as much as they should. Software engineers don't use it as much as they should, but it's kind of slowly getting traction. And then causal inference is used, but not much. That's all I have. Thanks.